Hi, my name is Malte. I'm an engineer at StackRox, and today I'm going to talk about talking to Go gRPC services via HTTP1. That's a problem that I recently had to solve at StackRox, and I want to jump right in. At StackRox, we're building an application which is deployed in the Kubernetes cluster running in our customers. And our application is based on a microservice architecture. So we have a fleet of microservices deployed in the Kubernetes cluster, and those microservices talk to each other, and we're using gRPC for that communication. This intra-cluster service-to-service communication using gRPC works great. However, we are also using gRPC to communicate from entities outside of the cluster to services running inside the cluster. For example, we have a command line utility called rockscuttle. And for this command line utility, we're also using gRPC to talk to our backend service. And in such a setup, the traffic from outside of the cluster has to enter the cluster, and it typically does that by using a load balancer service or an ingress controller. The problem with such a setup is that basically it boils down to gRPC being based on HTTP2, and a lot of load balancers don't like or don't support HTTP2. More precisely, I'm talking about level 7 or application level load balancers. The most prominent example of such a load balancer is ELB by AWS. But there are also like some other load balancers which have problem with HTTP2 and gRPC, such as nginx in older versions. What can we do in such a scenario? Well, there are a couple of options. We could opt for TCP-only load balancing. For example, if we use a TLS encrypted connection, we can configure it to use TLS pass-through, in which case the load balancer would not terminate the TLS connection, but instead just forward the bytes one by one from the client to the server. We could also use a load balancer that supports HTTP2 between the client and the server. The L7 load balancer available at Google Cloud Platform makes it possible, for example, but also sufficiently recent versions of nginx or HA proxy. There's also a module for Envoy, the Envoy proxy, which is called the gRPC HTTP 1.1 bridge. This is actually pretty similar to the technique I'm going to present in this talk. The main reason why we didn't opt to use it was we felt it was too heavyweight to kind of like spin up an Envoy proxy sidecar for all of our services. We don't assume that we run in an Istio environment necessarily. And I also put an asterisk next to viable because those are the technically viable options. That doesn't necessarily translate into practical viability. Our customers might be more or less opinionated on what technologies they want to use for exposing services. And if we tell them they can't use ALB, which they use for everything else, and that they need to use TLS pass-through and can't use managed certificates in their infrastructure provider, they might be less than enthusiastic about that. So the functional requirement for the solution that we are looking for is to replace the gRPC, which is used in a rockscuttle CLI, with something like gRPC that works via HTTP1. Preferably, it would be something that's just as nice to use and just as reliable as gRPC. There are also some compatibility constraints. Obviously, the new functionality of being able to work through a gRPC incompatible load balancer only needs to be available when using new versions of both the CLI and the server. But we can't always expect our customers to upgrade the software in lockstep. So if they use a combination of a new CLI with an old service or vice versa, this should at least preserve the existing functionality of working through a gRPC compatible load balancer. One thing that, for example, precludes us from just switching to a different RPC protocol altogether, because that would only be supported in the new software and not in the old software. So the first idea we came up with was to use REST APIs, and that sounds a little bit like a contradiction to what I just lined out as a compatibility requirement. However, we have REST equivalents for pretty much all our gRPC APIs throughout the product, thanks to the gRPC gateway, which automatically takes care of the translation. What it would look like on a technical level, we have our CLI, and that CLI makes a request, a gRPC request, which technically is an HTTP2 post request to the server, and we specify the respective gRPC content type and encoding scheme, usually protobuf. And instead of doing such an gRPC request, we instead do a plain HTTP 1.1 REST request, for example, to a v1 metadata REST endpoint, and using JSON as the encoding scheme for all our payloads. To use that on the code level, our idea was to use proto-C gen Swagger to generate open API specifications from our gRPC service descriptions, and then generate Go bindings for these open APIs back using Swagger code gen. We weren't really thrilled with the result. It would have required lots of changes in our code. It would also kind of has led to a duplication of our data structures. Instead of using protobufs everywhere, we'd also be using the open API generated data structure somewhere. We also found some bugs in the generated code. In all fairness, that might well have been due to a user error. I didn't dig too deeply because it became apparent pretty early on that we should find a better option that is less invasive in the changes it require. So for finding such a solution, an important first step would be to look at some background as to why gRPC uses HTTP2 and what HTTP2 actually entails. The difference between HTTP2 and HTTP1, some of these differences are performance related. For example, HTTP2 is based on a binary format, and it also supports multiplexing of multiple streams onto a single TCP connection. Those are advantages for performance. On the functionality side, there is support for full duplex client streaming. That's important for some RPC calls. And there's also support for trailers in HTTP2. And there are also some other aspects in HTTP2, such as server push. It's really not relevant for this presentation or even for gRPC at all. So the first aspect we want to take a look at is client streaming. Client streaming basically means we can interleave the request flow between server and client. In HTTP1, the client talks and then finishes talking, sends all the data, and then the server responds. In HTTP2, the client starts talking by sending a request and request headers, and then the server may start responding at any time, regardless of whether the client still has more data to send or not. gRPC uses this for client streaming RPC calls and bidirectional streaming RPC calls. Client streaming is actually a pretty significant step in terms of functionality over HTTP1. You cannot emulate client streaming in HTTP1. You would need to resort to a technique such as WebSockets in order to do something similar. The good thing is Rockscatter CLI only uses unary RPC calls, so no client streaming required. The second aspect is trailers. Trailer method is metadata sent by the server after the response body. You can think of trailers as kind of like deferred headers. The typical use case for trailers is to calculate a checksum on the fly of a response body without having to buffer the entire response body on the server side before sending it back. gRPC uses trailers in order to communicate status, information, and error messages. For example, think of a server streaming RPC call. The server sends a message after message until eventually a deadline expires, and then this deadline expires status should be transmitted to the client. So even though the server has already sent data, the server can still indicate that the request failed, and thus the status needs to be transmitted, cannot be transmitted in the headers, but needs to come after the response body. The advantage here is that trailers are not significantly different from anything HTTP1 offers compared to client streaming. They are on the HTTP protocol level, but if we can assume that we can make modifications to the application level protocol, we can just embed trailer information as part of the response body, just appended to the original response body. And that brings us to gRPC Web. gRPC Web is an alternative transport specification for gRPC, specifically targeting web clients such as browsers. In gRPC Web, you have support for unary and server streaming RPCs, so client or bidirectional streaming are not supported due to lack of HTTP2 features. And in gRPC Web, trailers are encoded as part of the response body. So gRPC response body is a sequence of messages, and in gRPC Web, the trailers are contained in a specifically designated message, which is sent after the last message of the server response. It sounds like this is exactly what we're looking for, and it would solve all our problems. Unfortunately, it's not quite that easy. I wasn't able to find the Golang-based client library for gRPC Web, which we would have needed to use on the CLI side. There's support for gRPC Web in the Envoy proxy, but we cannot expect the Envoy proxy to be present in our customer setups. There are also standalone proxies for gRPC Web and translating between gRPC Web and gRPC, but deploying them in front of application breaks compatibility requirements because, again, it will require our client, like all of our clients, to use gRPC Web requests. So the solution we came up with is what we call automatic gRPC Web downgrading. And this is, instead of just using gRPC Web for everything, it's an adaptive technique, which works by the client sending a regular gRPC request to the server, but also indicating that it is able to accept and process gRPC Web responses. And we use the standard accept header to indicate our readiness for that. And the server looks at an incoming request, and if certain conditions are met, it decides that the response will be sent as gRPC Web and not as regular gRPC. And those conditions are, on one hand, the ability of the client to accept gRPC Web responses. That's communicated via the accept header. We also look at the HTTP protocol. If the HTTP protocol major version is 1, then probably there's an incompatible proxy in between. And the more reliable indicator is the TE header. TE stands for transfer encoding. And if all the proxies are compatible, the TE header will have a value of trailers. If there's an incompatible proxy in between, this TE header will be stripped. So making a gRPC request from a Rockscaler CLI to our backend service, we start the regular gRPC request as a HTTP2 post request with a TE trailers header. Assuming a compatible proxy, this request gets forwarded as is to the backend service. We have HTTP2, we have TE trailers. Everyone is happy, the server is happy, and can respond with a normal HTTP2 200 OK gRPC response. What happens now if we have an incompatible proxy in between? So if we have a proxy that drops the TE trailers header, well, in that case, and also we assume it downgrades the connection to HTTP1. We don't have a TE trailers header. We don't have a HTTP2 request. The server doesn't know it can't process this request in a normal gRPC fashion. The server is unhappy, and it just will send back an error response. Now, using our automatic downgrading, we modify the client to inject the accept header on the client side. We say accept application gRPC and also application gRPC Web. Accept is a standard request header, and the proxy will forward this header to the backend. Note that the backend still sees an HTTP1 request incoming without a TE trailers header. In that case, however, we see the client is able to accept an gRPC Web response. Server is happy again, and it can send back a gRPC Web response. The client, having indicated so, can also process this gRPC Web response, and the client is happy as well. How did we go about implementing this functionality? On the client side, we spun up a local reverse proxy. That's actually very simple to implement in Go. There's a reverse proxy utility type. The reverse proxy modifies the outgoing request by injecting the accept header, and it modifies the incoming responses by transcoding the gRPC Web payload to regular gRPC over HTTP2 traffic. And it does so by detecting gRPC Web payloads through the content type header sent by the server. This transcoding effectively means we look at the last message in the stream, we verify that there's a trailers message, we pass the trailers from this message, and we forward them to the client as actual native HTTP2 trailers. What's also relevant to consider in the setup is that the connection between the application and the reverse proxy uses a local in-memory pipe, so it's not hijackable, and thus we don't TLS encrypt it. The reverse proxy needs to intercept the request anyway, and then the reverse proxy makes an outgoing TCP connection with TLS encryption, and that even allows us to, if we have a direct connection to the remote peer, to use client certificate authentication, because TLS really only starts at the reverse proxy and is not terminated or man-in-the-middled in between. On the server side, we use a feature from the gRPC server implementation which is that the gRPC server supports or offers the serve HTTP method. That's a standardized Go HTTP server handler. It handles a request and it writes back a response. And we wrap the server handler by adding logic to see if we need to do gRPC Web downgrading, and if we can do gRPC Web downgrading. So we test for the presence of the accept gRPC Web header and for the absence of the TE trailers header. We modify the request to fake an HTTP2 protocol information and also to re-add the TE trailers header. And that is to kind of like prevent the gRPC server implementation from complaining about a malformed or not processable request. We also intercept the response writer for this server handler such that it will transcode HTTP2 trailers into trailers sent as a message as part of the response body. And then with this modified request, we make a delegate call to the original gRPC server serve HTTP implementation. So showing this in one picture, I have to apologize for the low resolution of the picture. I didn't have the raw materials anymore. The client makes a HTTP2 post request to the reverse proxy. And again, this is slightly outdated. We no longer use a localhost TCP listen socket, but just an in-memory pipe. And the local reverse proxy injects the accept gRPC web header. It goes to the proxy. The modified handler on the server side basically replaces the protocol information from HTTP1 to HTTP2 and strips the accept header. The server is happy about the request. There's also the TE trailers header, which is injected, and it sends back a normal gRPC response, which then gets transcoded by the handler to a gRPC web response. And the gRPC web response reaches the local client proxy and again gets transcoded to a gRPC over HTTP2 payload, which the original vanilla gRPC client can consume. So if you think that's cool or think it could be potentially useful, we decided to publish this code as an open source library hosted on GitHub. It's written in Go, so you will only be able to use it if you use Go for both your client and your server. Where that's not true, you can use it on either the client or the server, but you won't really get any benefit out of it if you're not using it on both sides. But at least you also won't break any compatibility if you use it only on the client or only on the server. You can install it with a simple go get command, and the source code is hosted on GitHub and published under the Apache 2 license. Now I want to give you a very brief overview on how it used the library. So the first example is showing you how you would use gRPC normally without our library. You have a TLS configuration, you have some dial options for establishing the connection. You would call the gRPC dial context function. You give it an endpoint, transport credentials, TLS, and connection options. And then from this gRPC client connections, you can instantiate service clients, do RPC calls on the server, and eventually also close the connection. Now, when using our library, the code doesn't change all that much. You import the client package from our library, and then instead of calling gRPC dial, you call the function client connect via proxy. You still pass it the connection context, an endpoint. The TLS configuration becomes a first class configuration option. It's not just another dial option. But if you have other dial options, you can also pass them to this function, just as we pass them to gRPC dial. And the return value of this function is a normal gRPC client connection. You can use that in the same way as you use the one obtained with gRPC dial. You can use it to instantiate a service client, make RPC calls, and you can also eventually close it in the same way. And if you close this connection, the reverse proxy, which runs in the background, will also get automatically shut down. There's no need to do this explicitly. On the server side, the example I have is pretty simple and very stripped down, and it actually won't work like that out of the box, but yeah, just to give you an idea. You create a new gRPC server, you register your service handlers to this, like the echo server in this case, and then you call gRPC serve with a respective listener. In this case, we listen on port 8443 with the TLS settings. When using our library that injects a gRPC web downgrading handler, you would start with creating the gRPC server in the same way. You register your service handlers, but instead of having the gRPC server directly serve network connections, you create a Go HTTP server with a handler which is populated by calling the create downgrading handler from our library. And this create downgrading handler function returns an HTTP handler, which does the gRPC Web downgrading in an adaptive fashion. You pass to this function the gRPC server object and possibly also another HTTP handler. And it can be used to multiplex the same port for gRPC and plain HTTP traffic. You don't need to use that. You can also just pass nil here. And then you have that HTTP server serve network connections. They can also be TLS enabled. And that's really it. And then you're basically ready to go. You won't be able to use client streaming calls, but you can use unary and server streaming calls, and no further changes required to the application code. Before I conclude, I just want to talk about 2 lines of future work that we're planning. The existing code is not really performance optimized because the usage is not performance sensitive, at least not at a kind of like individual RPC call overhead. We definitely want to do some performance optimizations, and one idea that I have is to basically do an auto-sensing request to determine if we actually need that proxy on the client side, or if we can just bypass it because we know that the connection is going either directly to the remote peer or only through compatible proxies in between. The other line of work is to support client streaming and bidirectional streaming RPCs. As I said earlier, that is generally client streaming is not possible over HTTP1, but we could use WebSockets. WebSockets are generally wider supported among proxies and reverse proxies. For example, AWS's ELB does in fact support WebSockets. And by using WebSockets for the connections and implementing a gRPC over WebSocket logic, we could actually also realize client streaming calls. That's work that's actually actively ongoing, and it's being implemented. It's already implemented in our product offering, and we are currently working on upstreaming this to the open source repository to make it available for everyone. This concludes my talk. I want to thank all of you for listening. I've added here my email address in case you have any questions or feedback or comments or maybe ideas, feature requests. You're also welcome to use the GitHub issue tracker for leaving this. The URL is I've printed here at the bottom of the slide. Just file a feature request or a bug, or just drop a note to saying that you found it helpful. And that's it. I want to thank everyone for listening again. Good night.